When will humans land on Mars? This is something that we've been dreaming about for a long time. And now with new propulsion systems, with new robotic exploration of Mars, we're getting closer and closer to that point when we're going to see those first footsteps on Mars. But where will they go? Mars is an exciting place to visit, but it's also very dangerous, hazardous. There's long delays in communication, and choosing a landing spot to go to is very important to start building up the logistics and infrastructure to support long-term science base on Mars. So working on this problem is my guest today. His name's Rick Davis. He is the Assistant Director for Science and Exploration at NASA's Science Mission Directorate, and he leads the team who is working on selecting landing sites on Mars for a future human mission to Mars. So obviously it's a very complicated process, very nuanced. A lot of ideas are in the works, a lot of challenges, and some surprising requirements to find a place to land on Mars and to be able to start to study the red planet with human beings. It's a fascinating conversation. One of the best I've done. I'm sure you're going to really enjoy it. Rick is deeply knowledgeable and had a lot of really interesting insights. So enjoy the interview. Like, I know people want to go to Mars, and if they want just like to get a sense of what it would feel like to stand on the surface of Mars, what is the most Mars-like place on Earth?
Oh, there are actually a bunch of them, and that's really cool. We have work underway looking at a lot of these sites right now because we can actually go practice operations with rovers on these places. And so just to give you some, the Gobi Desert in Mongolia is one. The Atacama Desert is another. I've actually been hiking up volcanoes in Ecuador where you get up a certain level and the soils all have that sort of rust color that Mars has. And I mean, it's really pretty dramatic. And so there are a number of really good sites. We call them analog sites all across this planet. We use them for different reasons. One of the best ones actually is in Antarctica in the dry valleys. And that if it weren't so difficult to get there, a lot of our work would be there because it is essentially a desert. It has ice sheets. Mars has ice sheets, and it's just got a lot of the same temperatures are extreme as they are on Mars. And it's really an amazing site for being in a Mars-like environment.
But even Antarctica, like the dry deserts of Antarctica, which is one of the most hostile places on Earth, that's a paradise compared to actually being on Mars. So then if you were actually transported on Mars that reminded you of the dry deserts of Antarctica, what else would you be experiencing being in that place?
So there's a number of things. So just to give you some, for example, the pressure at Mars is like being at 135,000 feet in our atmosphere. I mean, it's basically almost a vacuum. So it's not like you're going to take off your suits. I mean, you're essentially in space in that regard. Mars has the potential for biology, which is on one hand super cool. On the other hand, could be a risk, right? And so that's another one. Another sort of in the difference is that Mars can get really cold, and down at the equator, on a warm day, it can get up to freezing, and then it can drop 120 degrees at night. It's further away, and so like in the more northern latitudes. Planet is tilted, so its winters tend to be more severe, but it gets so cold up there that carbon dioxide, freezes out, and you get snow there, and lots of it. And so it's a really different kind of place. It's a lot of times people look at those pictures coming in from Curiosity and they think they're in the Atacama Desert or they're, the Gobi Desert or whatever, and it's really misleading because it's really more like going up K2 or Mount Everest times 1,000, and if not 10,000, and that's where the right mindset, where you might have a few frozen bodies along the way, because it is really dangerous. Now, having said that, human beings have learned to go up Mount Everest and K2, and they will do so more. They will learn to get all the way out to Mars and essentially create human civilization out there. It won't look like it does here, but on the other hand, it'll have many of the exact same attributes that we all come to expect here on this planet.
And I guess the other weird experience would be that lower gravity.
Yeah, so that's actually a really fun one, and I would say, it's 1/3 the gravity, the moon's 1/6 the gravity. So in a nutshell, what that means is that when you jump, you're going to jump a lot higher. I mean, when you get right down to it, that actually can be problems because, like on the moon, the suits were kind of awkward. And if you watch a lot of the video of the people who walked on the moon, they fell all the time because they're essentially, their the center of gravities aren't right, and then they're bouncing higher, and so that will be a challenge. The in-space piece is also fascinating for getting out there because it takes about 6 to 9 months to get all the way out to Mars. And then on a lot of the trajectories that people look at nowadays, they generally assume that you're in the Martian system, either in orbit or on the ground for about 500 days, so the planets can line up, and then you have another 6 to 9 months to come back. And if something goes wrong and you can't land for whatever reason, or if the initial missions are just orbital missions to kind of get our sea legs on doing this, if you will, space legs, I guess, that you could be in space 1,100 days. And so how the human body, handles zero gravity, how and there are big problems, muscles atrophy when you're in space, bones start to decalcify because bones need to be exercised. And so how, we think we can handle it on the space station for a 6-month cruise, but how does that work for a 3-year mission? That's going to be, there's some real work to be done to kind of really close those gaps in our understanding.
So let's talk about the criteria for a place to land on Mars. I guess, how long have people been thinking about this problem? Because I know I've read books, as a child, 40 years ago, with people proposing different interesting places on Mars that would be a great place to send human explorers. Mm-hmm. How has the history, I guess, of this search? Can we talk about that?
Yeah, that's a really fun topic for me because we're learning, Fraser. I mean, and part of this is just iterating on it and it's a lot of detective work. And I'll give you some examples of it. So first of all, we've been landing rovers, for decades now on Mars. I think the first one went out in the 1998 timeframe, if I recall correctly. And there goes a lot of work to try to figure out where you can land these things and a lot of this work, and then where you're sending it so that it's scientifically interesting. So the two things for a while when we landed at Mars, there wasn't, our accuracy on landing wasn't super great. And so you really had to pick areas to be careful about hitting rocks when you actually are landing. And so that kind of constrained the science that we could do. But science is the other big driver here. When you go there, you're on another planet. We want to learn about it and want to do civilization changing science. And so picking really cool places. So as we've iterated along, we've become much more precise on where we land, which in turn, Fraser, allows us to pick even cooler places because we can go there, and despite the fact that there might be rocks or cliffs nearby, as long as we can precisely land, then we can actually drop in a more interesting place. And so, and we've gotten better and better. Now, when humans go, it's even more 5 times, if not 100 times more interesting problem because there are a number of things you want to be thinking about. One, you want to make sure that when they land that you don't hit rocks or anything like that, the same hazard avoidance things that you want to be concerned about. But that's pretty simple because with human space flight, we're going to have beacons. We're going to be able to pinpoint land these things, and that I'm absolutely certain. So then other drivers, to give you just some of them, is I think we learned from the Apollo missions that when you go, you really want to be building up infrastructure. Space station has actually taught us this. When we put spare parts up there, we put spare food, all that kind of stuff. They did this in Antarctica too. They have McMurdo, so they have ships that can get in there. They bring in spare supplies, spare food, everything. Because when a bad winter hits or things break, you want to be able to handle that. And Mars will be no different. So you're going to want to pick a place, probably aiming for it to be a semi-permanent base so that you can stockpile things and start building up habitats and rovers and that kind of thing. And so really getting a place that is interesting and that allows you to do that is key. So some of the factors that matter is that to drive the cost down of missions to Mars, you really want to be producing propellant locally at Mars. And so the most likely propellant sources will be methane, and oxygen as the oxidizer. And so you can make methane as long as you've got a carbon molecule and a hydrogen. And so getting access to water is really important for picking these sites and making sure you can produce a lot of water so you can make methane. And then oxygen can either come out of that process or you can pull it out of the atmosphere. We have the MOXIE experiment right now, and it is producing carbon dioxide. It is producing oxygen from the carbon dioxide atmosphere. So we're already learning to do that. But the next step is to figure out how to produce water. And then, so that's probably the big one, but over time we'll want other things. No doubt we'll try to figure out which minerals and all those kinds of things are there to support operations. But the other one is that we want to do really cool science. And so that's something that our directorate really worries about, is picking sites that are just amazing. And so the frontier at Mars has really been focused on following the water. And that's really what we've been doing to try to understand whether or not, for example, Mars had life. Now we are moving more towards accessing the subsurface and the subsurface ice. Mars actually had oceans and rivers and glaciers, and a lot of that water is actually still there. It's just, you can think of it simply as largely covered in dirt, or as they call it, regolith, and dust, and it's buried there. But we know that there is major deposits of water or ice there. And my suspicion is that will end up being a driver, but for science, it's definitely a high priority target, because you can drill down into that and you get a snapshot of the climate at Mars over time. And there's a lot of belief that if life existed on Mars, it migrated down into the subsurface and is to escape things like the radiation environment. And we see life moving into really extreme locations like that in Antarctica. Antarctica is actually really good in terms of teaching us. Life forms exist inside rocks, to give you an example, in Antarctica.
Right. Hopefully we'll find that on Mars.
Right. And so the idea is you try to pick a spot where you could really do this kind of research. So you can imagine when crews go there, it's hard to do it with a robot, but you can imagine that when crews go there, we may have them drilling, deep into that, so that we get that snapshot, of the climate there. We get to see whether not we can detect life, and that's probably going to end up being a major priority for scientists and our scientist explorers when they land on the planet.
I mean, when I think about, say, the large scale parts of Mars, I mean, you talk about this need for water. Well, we know there's tons and tons of it at the poles, as much water as you could ever need. And it's sitting right there on the surface with the polar ice caps. But maybe it's a more hostile environment with colder temperatures, maybe less interesting for life. So is there I'm trying to think, where do you put your finger on the scale on either side?
Well, we need a lot of,
I've heard a lot of proponents who say, no, the poles, start at the poles because you got the water, and the water drives the whole thing.
So there's a lot of things that factor in there. So a couple of them, just to give you a sense of it. In the ideal world, you'd want to be down at the equator from an engineering standpoint, because the spin of the planet actually helps you launch. You essentially are using that speed of the spin down there to do that, and that reduces how much propellant you have to produce locally, and it just makes it a lot easier. It's also warmer down there, and so that's, the humans are going to be in suits, and they're going to be in habitats and rovers. They're not going out for a walk. Right, for the reasons that we talked about. But the machines do better when it's warmer. And so being down the equator would be ideal from that perspective. The problem is that when you start looking at water sources, the equator is warmer and therefore drier. You can think of it simply. And so there is a sweet spot somewhere that we probably end up looking at, which is probably in these mid latitudes, like 30, 35 degrees north, something like that. And there are a lot of other places where we have these ice deposits, but they tend to be further, a little closer to the poles. But you still get a lot of that spin effect, and the temperatures are not that bad. And those are the sort of the drivers I think that we'll end up on. We're going to need a lot of creative people helping us figure out where that initial base goes. Because the equipment is so expensive to get there that you're probably not going to do multiple landings and not build up that infrastructure. And they're so far from any support systems, at the Earth, that it's even more important that you really think through a logistics supply buildup. Space station, is really a great analog in that regard, but it is different. That on space station, if something goes wrong, you can undock and get back on Mother Earth really quickly. If you're on Mars and something goes wrong, it could be years before someone that movie, The Martian, is not too far off. In fact, we work closely with them. It's not too far off in that regard, before you get help. And it's not, and you can't even just talk to people and say, help me with this easily, because I used to be a capsule communicator for the space station, and we would sometimes say, put a camera right over your shoulder, and we could actually help them walk through it real time. We'd even bring the smart people in and say, why don't you talk with them directly, and we'd walk them through it. But when you're at Mars, to say, hey, I got a problem. If the planets aren't in the right place, that can take up to 22 minutes just for hey, I got a problem, to get all the way back to Earth. And then, for assuming we're listening, right? And then we have an answer for them, then, the answer is probably going to be stand by. That standby is going to take 22 minutes to get back. That's a 44-minute round trip in the worst case. And so, that makes the importance of logistics a lot higher in my mind, and in many respects, this isn't new. We deal with it on the space station. We dealt with it down in Antarctica. They learned through the School of Hard Knocks, even in the early days of exploration, including Jamestown and a number of other places, that you can live and die by logistics. And that's, so building, finding the people to pick a place that is, has the right resources that we need, and that is compelling from a science perspective, sort of drives that. And then you're probably heading towards an initial base that you will then branch out from and explore further from there. And I think history points us all in these directions.
Yeah, it's interesting. I mean, I think people's expectations when those first astronauts go to Mars, and even when we watch TV shows and movies and stuff, often they're right out there with their drilling rig and looking for the microbes, trying to find the water, whatever it is. And it feels a lot more like it's going to be so much time spent just securing that foothold, that all the work is going to be in making the place safer and more redundant for a long time before you can really feel safe enough to get outside and start to do some of that interesting science, because the safety of the astronauts is on the line.
So I totally get that perspective, and I get that. But I think we've learned with exploration efforts in the past that we can do both. The trick is to think through it sooner than later. So right now, it's actually very exciting, because there are a number of efforts underway to actually look at what the high priority objectives are for when humans land on our second planet. And so that we can start figuring out how to do it, and then get it done as efficiently as possible so that they do have the time, for example, to do what we call assembly and checkout. But it just basically means hooking stuff up, making sure it's all right. And there's a lot of work. Your surmise that that's a big time consumer is exactly right. That on the space station, we spent years, hooking that stuff up. We were doing some science in that time frame, but it is a lot better now that all that initial hookups have been done. And it's going to be key. And I think that we'll have to really think through that so we can make sure it's as easy as possible for the people that will be there to get it done. But I am absolutely convinced that those first crews will be bringing back significant amounts of samples from this new planet. And it will be transformative in terms of our understanding of how planets and therefore how our planet works too.
So what are some surprising challenges that maybe people aren't familiar with for choosing a landing site on Mars or actually going through the landing?
So there's that's great. So let me do it in two parts. Number one, we'll do other things that are challenging about finding it, and then secondly, going through the landing, because they're really two different things, and they're really cool.
Yeah, of course.
Yeah. So let's just give you some on the idea of what it takes to picking a spot. So, for example, right now when we sent we have a satellite in orbit around Mars right now with a radar, and that radar was not intended to look for ice sheets. It was looking for deep aquifers. So we chose a frequency that is looking for these lakes of underground water way deep. We had no clue that we were going to find these ice sheets right next to the surface and sometimes popping right up. And in fact, at Mars, you can actually, now that we've gotten smarter, we can actually see meteorites hit Mars. And then when they hit, they strip the dirt away, and then you can see pure water ice there. And we weren't expecting to find any of that. And there are real gaps in our knowledge as to exactly where those ice sheets are and how close we can get them to the equator that we're working to plug in terms of those gaps. There is actually another source of water, which is called hydrated minerals. And these are basically dirts and rocks that have water molecules or hydroxide or OH molecules in them. It's a little difficult to envision producing large amounts of water in an efficient way from an energy standpoint with that. So my suspicion is we will end up using these ice deposits that are just begging for it. So we need to understand where they are better. Another thing is Mars has these global dust storms. And so, for example, we had one that killed our amazing rover Opportunity. It had been that mission was supposed to last, I think, about 3 months, 90 days, and it ended up being like 15, 16 years. It was a long time. It was incredible. But what did get it is that it had solar arrays that it was using for power. And we had a dust storm that occurred at Mars that lasted, for almost 7 months, basically. And it's so severe, Fraser, that it blocks out a lot of the sunlight, and it just couldn't produce power, and it batteries discharged and it died. So a couple things. One, you want to pick places where there aren't dust storms all the time. There are places that have more dust storms than do. We need to understand weather there better than we do. We can't predict it right now. We can't predict. We know that in certain seasons the dust storms occur more, but we can't say it's like you can see a hurricane, right? You can see it forming, and then they can predict where it's going and that kind of. We don't have that kind of predictive quality with weather at Mars at all.
And it's tricky to steer clear of a global dust storm.
You can't.
It's everywhere. Yeah.
Yeah. And so that's one problem. The second thing is Mars has these big, because it's basically transporting dust everywhere. It's got these big areas where it's got just big like things of dust, and you don't want to be operating in those areas. So we can measure that. We can actually find places that don't have that. for landing, to give you an example. We also want to be able to land. We're not going to have landing pads and that kind of thing for a while. I'm absolutely convinced we will, but initially we'll be landing. And so you want to be landing on stuff that can bear these big rockets coming in and throwing flames out. So understanding where bedrock is really important. So these are all examples of things, and it's not a terribly long list. And I think we're rapidly getting a good handle on those things, and many of which we're actually getting smarter about day by day, that will help inform that. So I think we're actually doing a decent job of getting there. There's a lot more that we need to learn, but between the United States and a lot of other countries that are aiming towards Mars, I'm pretty confident or optimistic that we're going to get it before we're ready to send crews. And then in terms of landing, I do want to talk a little bit about that, because when you land, so a rover right now weighs about a metric ton. It's basically an SUV. And so when we do some really funky things to land that thing. You got big parachutes that open, and then you've got this thing called a sky crane, which is basically kind of holds the thing and then it drops it on a cable, but it's got jets firing so you don't dig out holes in the thing. And it is a tribute to all the people who came up with those landing capabilities, but they're hard. For human class landers, they're at least 20 times that size. And so parachutes, the general feeling is we've exceeded the capability of parachutes to really help with that. And so the way you do it is you basically come in and you are firing jets, which they call supersonic propulsion. And then you're actually trying to dip down really low in the atmosphere, so that you have as much air. Because remember, I said it's like being up at 135,000 feet in our atmosphere, even at the surface. And so you want to dip as low as possible, go as low in terms of altitude as possible too, so that you can get enough air to help slow you down. And you're doing all those things. So if you look out the window, it's going to be a pretty Yahoo ride when you come in.
Sounds pretty terrifying.
You're going to be close to the ground screaming. I think we're quickly getting there in terms of learning how to do that, but we have a lot of work to really nail that. But so the point is, then you have this big thing that's got jets that are slowing it down. These are like really big rockets, and so they will tend to dig out. It's basically that, and it's throwing dirt at 3-4 times the speed of sound, dirt and rocks. So we have to really kind of think through how you manage that, because that rock is like a bullet when it's going. And if you've put habitats down there, or rovers, and you've made a really big investment to get them there, the last thing you want to do is go riddle them with a bunch of bullets. And so but these are largely, I think we understand the problems well enough that we can do it. And eventually you will see things like civil engineering coming into play on the second planet in ways we've never even thought about it. You're not going to make concrete at Mars, but there are some really creative ideas so you can actually create a surface that can better handle those loads and that heat. And the acoustical energy of rockets coming down there. And I'm convinced we'll figure all those things out, but they're really cool problems to go solve.
Yeah. With the coming in sideways,
yeah.
I guess there are ways. I don't know of anybody testing I know that various spacecraft have done some aerobraking, they tested aerobraking on Mars with some of the missions that went to Mars. It's been tested, I think, on Venus. But I can't think of anybody testing something like Starship, and maybe that'll be a future test on Starship. Is they'll come in at 135 feet of altitude, hit the atmosphere sideways, and see if they can if they can land in the air and then come down to the surface. Right? That'll be interesting.
So it's a reason why the United States was the only country for decades to successfully land. And Chinese have now done it, and I'm convinced that we'll see the Europeans there soon. But that is really hard stuff. And these are small landers compared to it. The ones we sent in 97, that's like university rover projects are that size. It's like literally this big.
Yeah.
These current ones are like cars, like I said, but these other things are not. These are big things, and
Yeah.
and
Yeah, and I know there's an issue. There's a risk with even landing these on the moon, that you land one of these big spacecraft on the moon, you're going to kick up regolith that's going to go into orbit around the moon and create a sandstorm that will then prevent any other spacecraft attempting to land. It's probably going to come back and pelt your spacecraft later on and sandblast. We don't know the impact, pardon the pun, of that. And so I think about that idea, like you've got these giant starships landing, trying to get close to your base, but far enough that the supersonic bullets that are blasting out in all directions aren't taking out everybody at the base. Like you want it on that, over that mountain over there. Like you want it on the other side of that ridge.
Well, no, that's exactly it. There. Yeah, no, that's exactly. So there's sort of the current thinking is that, you basically pick places to land that are, have a ridge, right? Like in a crater or something like that. Of course, that begs the problem. How do you get out of the crater, right?
Right. Yeah. Yeah. Like then you need a road, and then you got to get from where the landing site to your base. Like these problems just compound. And I'm guessing that a lot of these insights are dawning on the people working on these landing challenges are only possible because of the increased knowledge that you have. You have Mars Reconnaissance Orbiter, you have these various spacecraft that are studying the surface and the atmosphere and so on, and now you've learned more, and what a surprise, it turns out to be a more challenging problem than you had previously believed. So what is a problem that is starting to dawn on you that is probably going to be bigger than people had originally expected?
Oh, a fun question. Let me think about that one. I'll tell you one that's an easier one, maybe, and then let me think about because your question's a really cool one. So we definitely need to better understand where the water supplies are on Mars, and and the ice for science, for sure, and probably for ice for you. We need to do that. You have to have another radar go out there that has the right frequency to actually figure out where it is close to the surface. Now that we know that there's ice there, but that's mostly an engineering problem. So let me see. I think having two things I would say to more specifically answer your question. Number one is that I think how to answer this. The technology stuff I'm not so worried about personally. I mean, they're hard. We'll solve those. I think you start to see, the hardest one's entry, descent, and landing. I think anyone who's been thinking about this problem would tell you that. But I think we have a good path to do that. The larger issue is that it's a different way of operating, because these things are so far. Mars is so far away. You can't just call them. And learning to really allow those human beings to to provide the support systems with those kinds of time delays, and to help them not just technically but also psychologically and on so many other fronts is going to be something. And picking the right people to go, right? Because I would say I worked space shuttle and I worked at space station, and I would say for space shuttle those were 14-day, 10-day missions in that ballpark, and the priority was on usually getting the scientists there. And we didn't really spend as much time thinking about compatibility. When you talk about going on space station for 6 months at a time, though, you're in a different ball game, and we had to unlearn a lot of things. I mean, on a 14-day mission, anyone can put up with a jerk, but no one wants to put up with a jerk for 6 months when you're stuck in a can with them, and you can multiply. You remember that Mount Everest and K2, you probably multiply that by 1,000 for Mars, because the minute you burn those engines to go out to Mars, you're not seeing your family and everybody else you love for 3 years on a typical trajectory that we often look at. There are some options for 2-year trajectories, but that's still a long time, and so really, figuring out a way to help these crews, succeed, and also picking the right people and then giving them the right support systems is really, I think, going to be the coolest challenge here. And then, so that's number one. The other thing, which I would say is a soft skill thing too, which is that if you assume that one country is doing Mars or doing the moon, it'll be really expensive to do it that way, but it's going to be a partnered thing, and you're going to have partnerships of equals. And those are new kinds of relationships. I work in a group called the International Mars Exploration Working Group, where we have 28 space agencies, and these space agencies, almost a bunch of them have been doing space stuff for years, and they do some really bold things, Fraser. So you got to kind of learn to work with them and treat them like equals, and then count on them to do their parts, and then figure out the parts that work well in terms of letting them do it, and then make it a community of human beings effort. And we know a lot from space station and from other efforts, but I think it's gonna be a real challenge, figuring out how to do that going all the way out to Mars. But I'm convinced that to do it in any kind of time frame that I think any of us would aspire to, we're going to have to figure out how to do that even as quickly, and that's going to be a really an amazing challenge.
Yeah, it's interesting, that time delay. I think you mentioned that sort of early on in your answer to the question, and that 45-minute round trip time at the worst case scenario. It gets better when they're closest, but that time delay, I think, is going to be an insidious friction that percolates through every part of it, because I can just imagine someone's in a desperate situation and they're like, what do I do here? And then 45, and then you you tell them, can you ask him to remove the lens cap? And so it's 45 minutes for at least him to get an answer back that he needs to remove the lens cap. Then he removes the lens cap, and then it's another 45 minutes to get the answer. So it's an hour and a half when lives could be on the line. And I think and so you're going to need personalities who are very independent, very able to work efficiently without needing to be able to talk to the base camp, without needing permission for every single thing that they do, which is kind of anathema to the way NASA has worked traditionally. Like, when astronauts are on board the space station, they have a nice checklist and they're talking to ground control ongoing, and then so you're going to need to have people who can sort of deal with these situations, but then also be in a kind of a collaborative environment where you're trying to work as a team and so on, with that cut off. And I don't think that's a dynamic. I mean, we have submarine crews, and so on, but I think in general, in the modern era of space exploration, we don't have that kind of delay mixed with teamwork.
No, exactly. And it's a couple of points that you're spot on. And there are a couple of things I would add to that. First of all, on space station, with space shuttle, you had like that 10-day mission or whatever, something in that time frame. Everything is planned down to like the minute, Yep. And then on space station, we had to unlearn that, because we had crews, when you're there for 6 months, last thing any of us want is to have Big Brother telling us everything to do every minute. And so we had
time to go to the bathroom.
Yeah, that's right. Yeah. Okay, now you're going to smile for a public affairs event. And so we had to kind of learn to empower them to manage it, certain tasks on their own. So they have essentially like a job jar, they can knock stuff off. And we had to grow to that. And I would say that for thinking about Mars, you're spot on. I do believe that we're going to have to move aggressively towards artificial intelligence to help support these human beings all the way out there, because there's too much to remember. And computers are really good that way. And I think we're really going to have to start figuring out a way. I always call it put MCC in a box, but for those time critical things that you so correctly talk about, you're going to want to have a machine that is actually can do a lot of it for you and is maybe self-reasoning and self-learning, supporting you. I always say a nice HAL, right?
Yeah. But no pod bay doors.
That's right. And you're going to want that capability, because it's going to it could save people's lives. Mm-hmm. Without any question. And I think, there's a hesitancy in the space communities across this planet to move in that direction, because artificial intelligence systems are very dense computers. The chips are very dense, and so they're very susceptible to radiation damage. And so,
right, that does bring back up the HAL worry.
yeah. So there's like a creative tension there. But I will say that a lot of these commercial launch companies have actually solved that. They'll just have like 5 cores operating in parallel with modern computers, to do it, and they have a voting schemas, and we'll move towards that for these Mars missions. But I think having really advanced computing capabilities are key. And the only other thing which I would say to what you're saying, because your characterization of it is perfect, which is that you're going to have multicultural, multinational crews, and so people who are good not only in remote operations but also in multicultural team settings, it will be a very high priority, I believe. And you got to get the right skill sets, right? There. So, for example, you have to have a doctor because of that time delay. If someone's got an appendicitis, someone's got to be able to deal it, and then you got to be able to handle it if the doctor gets the appendicitis. And so there are a lot of smart people at Johnson Space Center and other places that are working on these problems, but they're really cool problems to figure out how you support them remotely. And you're right, the time delay is a big challenge.
Yeah, it's funny. Like I'm really fortunate. I get to interview a lot of astronauts, and when you do, you get why they were chosen. Like you're like, I see why you're an astronaut. You are so smart, but also really nice. Like I would be just glad to work side by side with you on problems for days on end where our lives are on the line. Like I can tell you've got my back and you're not a bully. And you know what I mean? Like it's going to be a good workplace. And I just wonder what the additional factor, that variable of the long delay times.
I don't think we know.
It'll add one additional personality requirement to these astronauts. They have to be super smart. They have to be really nice and work well together, but also be able to take leadership and handle pressure independently when things are breaking and they can't get any expert advice. They have to solve this problem on their own. And
so I would share this with you too, because at your spot, it's cool the way you've actually been doing all this. You're spot on about all of that. I would say we're not going to know everything. It'll probably, the first initial Mars missions will probably have some bumps that we're not expecting, but that's how we'll learn, right? The multicultural piece we've gotten a lot better about, because space station is multicultural, right? So we've kind of learned. There is another creative tension that comes into play, though, because on space station, when we had 3-person crews, sometimes it's because of language barriers or because people were picked because one country had 2 slots and then the other one had 1 slot, and so there sometimes getting the chemistry right was a challenge because of those things. When we jumped to 6-people crews, a lot of that went away, and so the number of people that go is important, not just for what you can do and have the skill sets, but there's just enough social interaction dynamics that actually allow people to have a more cohesive team, is the way I would say it. And I think in figuring out that sweet spot, because for Mars, every kilogram is going to matter in terms of pushing this up. So if you add another person, it's got food, you got water, you got to have, you got to have equipment for them to do science experiments. It's just this whole cascade effect that is somewhat correlated to the number of people that go. And so there is this tension about having the right number of people going by trying to make it affordable. And I think there's going to be a lot of interaction in terms of settling in on a number. I mean, right now we're assuming 4 people typically on our architectures. I've saw some of the 3-person crew, challenges, and I also saw how smooth it was that when you have 6 or more. And so I get a little nervous with a number 4. But I think
you'd rather see 6.
Yeah, I would rather, personally, with what I've seen, see 6. But I totally understand the orbital mechanics and engineering and cost problems with doing it. And so there's going to be a lot of discussion as we start converging in on architectures that allow us to go do this, and I think I've given you a sense of all the trades, but if you have enough human beings in the thing, even if there's one or two that don't get along, they have other people to do. And our entire experience in space has largely been 3 or 1 or 2. We have a fair number of earlier missions, but it's 3 or 6 or more. And 6 or more, if you can afford it, and that's a big if, Fraser. You can afford it, just get it, not only the social dynamics better, but the amount of work you can do is better. But you got to supply them. And so that's the trade.
Well, and talking about that supply, I mean, I think about all of the parts of the puzzle. When you look at, say, the station in Antarctica, I mean, they're at the point now where their infrastructure is so great that they're now growing food in the Concordia station, and they're at the point where they've got this indoor grow lights, and they're actually producing a harvest of strawberries and tomatoes and other interesting food, which I'm sure is a huge boost in morale to be able to go in there, but also to eat the food coming from that place. And that has only come after heating was figured out, transportation was figured out, like all of these basics were thought through. So, when you think about the technology that are required to live on Mars, to keep your astronauts alive, what again sort of haunts you? What is the thing? Like, I don't know, like when I'm working on a problem, the problem sort of shows up and just orbits around my head for a while going, this is something you probably want to think about. What is sort of, what are the outstanding challenges? You're like, I still don't know how we'll make a toilet work on Mars or whatever.
Well, fortunately, toilets, you've got gravity, so things go down.
yeah, but no plumbing, no water, no sewer system. But composting toilets, sure.
So, military planners will always tell you is logistics. I think it will be no different for exploration out to Mars, and I think that's. We are very focused on the technology. Tremendous work is being done at our centers and at other agencies, and even in the commercial sector right now. That gives me a lot of optimism about that. But I do think we need to think through the whole logistics thing so that there is so you have options, right? You want to be able to handle the bad day, and there will be bad days. On Mir, we had a fire. We've lost space shuttles. We're gonna have problems reaching that far, and so really thinking through how you have supplies, build them up, and how you can handle that. If there's one thing I think that we really will learn a lot from doing it. That in the original days of space station, we struggled. I mean, we would send stuff up, and then the crews would have bags. It wasn't really we didn't have a real plan as much as we probably needed, and so bags would be covering fire ports, and then the constant conversation was, where is this tool? It's not where you told me it was, and the frustration, Fraser, that comes from that, and so that's part of the logistics stuff, right? So that's like an inventory management piece, but then there's like getting it there and having it there, getting it there efficiently so that so you can use it to, drop your costs down, and so, I fully expect that you'll see solar electric propulsion systems that are like tugs, they're very efficient for moving stuff around. Ships are on this planet. Well, that's the equivalent of a ship or a tug in space, really. And, I'm figuring out how you mix and match those things so that you can really keep costs under control and yet provide the redundancy so that the crew members know that, if something goes wrong, like let's say, their food supply gets contaminated, they have options.
Yeah, I imagine that situation. You've got that artificial intelligence system with its 5 cores, and one of the cores gets hit by a cosmic ray and is offline, and for safety they have to remove that core and replace it with another. So where are the extra cores? Oh, they're over in the thing. Okay, great. Now grab your penta wrench.
That's right.
Wait, I don't have one. Okay. Right.
No, exactly. And there's a lot of historical examples of human beings screwing it up. Like in Jamestown, when the English first arrived there, they didn't really have a very comprehensive plan. And between 1607 and 1623, I'm always amazed. I think it's like 20,000 people went there. And at the end of 1623, I think 2,000 of them were alive. So they had like a 90% mortality rate due to starvation and not having, and picking a poor site and that kind of thing. And so, those are, I personally, in fact, I just went to Plymouth up in Massachusetts and that was actually a successful site.
Right. Yeah.
And Jamestown's basically an archaeological dig, so it's like you can choose well or choose poorly, but you learn from it. And really, the challenge for Jamestown was a logistics challenge.
Yeah, we have a similar version of that in Canada with when the Vikings came over and they started out on the east coast of Canada and didn't last. They left. They were here for a few years and then just couldn't hack it. Yeah. And went back to sunny Iceland.
Yeah.
Greenland. Right.
And then you have actually a more so it's there's a whole spectrum. The logistics supply chains allows you to handle the problems. And frankly, even if you don't pick the right people, but if you get the really superstar like LaSalle, who went I think he started in Canada and came down the Mississippi and actually made it all the way to New Orleans. Can you imagine the bravery of that guy and his team?
And that's the living off the land concept.
Exactly.
Yeah. And I think that mix, like I know a lot of emphasis is put on this living off the land of in situ resource utilization. You talked about getting your propellant, getting oxygen, pulling that out of the atmosphere and so on. How much of a mix do you think, like when will that really start to come online, do you figure? And how long will astronauts be eating packaged food?
I love
when
that
do you think
question.
the ISRU is going to come online?
So it's going to be iterative. I mean, I think in our current efforts, we're assuming that we're not using the ISRU for initial missions. We're trying to take it down, but you're going to want to do it because it's going to be so hard. You're going to need to go down in there. You need to get, drill into it, understand what you're really dealing with, because we've never chemically or biologically looked at those deposits. So just understanding it and then starting to set up the equipment is going to take time. I actually think that could be at the same time we start using water or even before. I think we'll start using the dirt or regolith to actually start making roads. In other words, we may be bringing binders with us that take this material and allow us to make hard surfaces, because it's, you could sort of envision that eventually rovers are actually, clearing roads, right? So that you're not having to go over the boulders we go over with rovers, right? Because that's really hard on rovers, or they may even be eventually laying down pads and that kind of thing. There's some really cool work being done in that regard. And I just think that using those local materials to actually do buildings, initially roads and landing pads, launch pads, however you want to think of it. And then eventually you doing it for building habitats and other spaces. You're going to want to do that, because bringing that stuff all the way from Earth is going to, and those are two obvious ones to me that I think that will be begging a lot of creativity to really figure out how you live off the land there. And then there'll be other ones, because we're going to find other things that we can't even think about right now.
So how do you think about planetary protection? Because, these landing sites on Mars they're interesting because there might have been life in the past, or maybe there even is life there today, and you've got ready access to water, but human beings are covered in bacteria. They would love a shot at a whole new planet. How does the possibility of planetary protection, how does that sort of work into your plans?
So first of all, it's a very important thing, and and as you're alluding to, and I would say there's two aspects of it. One, we call what we call forward contamination. We don't want to bring human biology, and human biology is remarkably Earth biology. Let me say it that way. It's not just human. Earth biology is remarkably adaptive. I've already talked about how it lives in rocks. It actually lives on the outside of the space station and basically vacuum. It is. It just does it. It's designed to propagate itself, and it's remarkably efficient at that. And so in the forward contamination, the last thing we want to do is bring life forms to Mars and actually, make it impossible to find life forms at Mars because we've overridden the system, overridden it with our biologies. So that's number one. Number two is what we call backward contamination, which is that we don't really want to bring the nasty Andromeda strain. I'm being a little facetious, back to Earth, because it's possible. Although I think a lot of people would argue there are two things: that the genome of a Martian biology is probably so different that it's probably not a relatively manageable risk. And then secondly, the crew is going to encounter that long before it ever gets inside the Earth's atmosphere on the way back. If you look at the Apollo astronauts, they were covered in dirt on the moon, and so the crew will be exposed to it. So there is sort of that built, and they have a 6 to 9 month transit back. So you're gonna see if there's an issue. That'll help. But the science, we want to preserve it. But on the other hand, in Antarctica, we do similar things. We are looking for what we call these life forms that have moved into the subsurface. We call them extremophiles. And the wind blows in a predominant direction. So, you make sure that your research areas are hopefully upwind of that, and you have ways of segregating the biologies. And I think we'll learn to manage that. And we have to be responsible with that environment too, which they are in Antarctica too. They don't want to just be dumping stuff all over the place. And so I really believe that both the forward contamination for science and the backward contamination will be manageable, but we have to think through it, and we have to minimize the exposures wherever we can. But you also need to realize that when humans go, the goal is to look for life forms, right? That's one of the goals. With a robot, it's hard to drill in these things with robots that have that time delays and all those other factors right now. When you have an astrobiologist and he or she is sitting on the planet with a drill and they can think real time, and they can kick the machine. I'm being a little facetious, but they can bring what humans bring to the equation. Our ability to actually find life forms there, if they exist, probably goes through the roof, using everything we've learned to date. And now we have the power, the dexterity, the flexibility, the intuition that a human, and the real-time decision-making that a human being brings to the equation, and the opportunities for discovery, despite the challenges of segregating biologies, which is what planetary protection's about. You have to balance that opportunity against the risks of the contamination. But the good news is Antarctica teaches a lot of those things to us already.
Do any of your proposed landing sites get really close to a lava tube?
So we did thank you for asking about that. We did a wonderful workshop in 2015 with over 400 people supporting it all over this planet. It was literally people all over this planet. And so the energy even surprised me. I think we've gotten that workshop to find a lot of research areas that we have been very proactively pursuing for the last 6 years. And I think we've gotten a lot smarter about things. And so I think you'll see that where we're looking will evolve as we get smarter and smarter. I personally, lava tubes are interesting from an astrobiology standpoint. I was recently hiking a volcano in Ecuador that has active, it was actually in the Galapagos, and they have active volcanoes. And so there were really, really amazing lava tubes. Some people think that that's a place to live, and I get why they're intrigued by that idea. But if you actually look at a lava tube and you were going to depend on it, the structure of it for your life, you probably wouldn't be super excited about it. But they are interesting from a biology standpoint, and I think you'll find us looking for them. But I suspect it won't be a driver in terms of where we go initially.
Yeah, when you think about trying to get down in there and set up your infrastructure, it's like trying to go to Mars from Mars.
Yeah, exactly.
Right. It's like the next chain of logistics.
Yeah.
So once the Mars logistics are properly set up, then you can think about maybe putting a research station in a lava tube. I totally get that.
Or have robots go into them. I mean, that's, people often frame it in terms of robots versus humans. I think all of us who have really been thinking about it realize it's not that. It's actually robots and then humans with their robots. And so, that means you can send little rovers down there. You might send helicopters into caves because, you could start imagining a whole set of variants that really allow the human beings to extend their range and also keep it clean, right? Because you could actually have a helicopter take an instrument, maybe eventually hundreds of kilometers away from where upwind, and then you could actually do research with it. And so the trick becomes how you utilize what the human's good at doing and what the robot's good at doing, and it's easy to sterilize a small robot, relatively speaking. And so it's really going to be a combination of those two that allows us to find these really interesting science targets.
Now, you came across my radar just because you wrote a fairly comprehensive blog article on NASA's website talking about just like the state of choosing a landing site. So where are you on this process, and what is like the next big deliverables that you're hoping to accomplish?
So I'd say a couple of pieces. We have just recently, so one of the inputs we got out of the previous workshop was that we really needed to understand where the water was. And so we have done we really pulled people from all across the planet to do mappings of these hydrated minerals that we've never had before. And that's very exciting and very insightful. A little discouraging in terms of that being a potential from my perspective. And then we had two teams. We had two teams doing that, 2 teams doing mappings of the subsurface ice using all the sensors we have to date. And that work is wrapping up. It's called the SWIM team. And that's actually represented a little bit in that blog. One of the next steps is going to be getting a new next generation radar out to Mars so that we can actually, now that we know roughly where the ice is, we can then go nail it down. Because the last thing you want to do is land, like the U.S. Decadal calls for like a robotic access of the ice first before humans get there. And in a mission that they called Emily, it was a mission concept they had. And there's a lot of reasons for doing that. But the last thing you want to do is put a lander down, have it with a 2-meter drill, and then have it hit a dry hole. So in the ideal world, we would do the next generation mapping of those deposits, and then we would send a robot to access it, and then we would be a lot smarter about where we put the humans that are there. There is a growing recognition that we need to understand weather at Mars better, which is exciting. But that takes 3 components. You have to have weather stations around the planet, and then you have to have sensors in low Mars orbit so they can actually see certain things. And then you have to have really what we call full disk views of the planet way up high. And if you have all 3, then you can actually start to build your knowledge state will grow so that you can actually start to do weather modeling and ultimately weather prediction. And that's really a key area, I think, going forward that you'll see more emphasis on.
We've known for a few years that Jezero Crater was going to be the landing site for Perseverance. I mean, it had been, after this very comprehensive landing site process, it was just considered the most exciting place to send a rover that's going to be looking for some kind of evidence that Mars was habitable in the past. So when do you think that we will know the landing site? When will the name for the landing site start to sink into our consciousness, and we'll be talking about it? Like, just think, in X years from now, humans are going to land right there at whatever, Utopia Planitia, or the top of Olympus Mons, or whatever. Yeah.
So first of all, for Jezero Crater, I do want to correct one thing, because there was a lot of debate about going into Jezero Crater, because there are a lot of hazards that are in there. And if you had said Jezero Crater is a very compelling site, as you're alluding to, but if you'd said that 10 years ago, I don't think people would have been on board with that.
Right. Compelling but terrifying.
Compelling but terrifying. Yeah, that 7 minutes of terror would have been times 10. However, we've gotten smarter. So we have something we call terrain relative navigation. So it actually has pictures. We take a lot of high resolution pictures, and the computer on board actually will recognize those things and then do very precision landings. And that was what was enabling for doing that. So there was a technology development, and then there was a recon piece, because you had to get all those pictures to be able to do that and to figure out where to go. But it wasn't, the debate about going into Jezero Crater was a very vigorous debate up till very recently. And I'm very proud of the Mars community, because in the end, the driver was, we've never been there. We're going to learn a lot from going in there, and we think we can do it safely. And so, we have a lot of tech development and recon to go do I believe, for picking really good human site locations. The good news is we're on the road on all of those things. We're advancing in all of those areas, and the lunar efforts will help significantly in terms of a lot of that tech development. And I think we'll iterate on it just like they did for Jezero Crater. I mean, they had like multiple landing site workshops, and they went from a fairly large list to a smaller one, then to a smaller one. And then the atmosphere, when they finally picked it, was actually almost electric, Fraser, because it's a really cool process. These people in the Mars science community, they're not shy. But you have to be a little audacious, right, to be thinking about doing stuff all the way out at Mars. And it was an exciting process to watch. And I have no doubt many of those same people support the human landing site efforts, and will even into the future. And I think but I totally agree with you. When we can pick a name for a place, how cool will that be?
But I wonder what, from when this, Perseverance was already under construction before its landing site was chosen. Right. It wasn't a lot before it actually launched that site was chosen. So do you think it'll be the same thing, that the crew will be selected, the hardware will be well underway, under construction, and a couple of years before the crew heads off, they'll know where they're going?
I think they'll know what type of place they're looking for, but I think the actual place won't be picked until that kind of time frame that you're talking about. And it wouldn't surprise me. I as a co-lead for the human landing site things at the agency, I always pick the spot and then that'll be it, right? And we can slap a cool name on it, but it's more nuanced than that. I think that it wouldn't surprise me if when the crews go there, we do what we call short stays, where you just go down to the surface. Because if you think about it, at Earth, we always say in space is dangerous. If having worked in a mission control room, I would say if there was a mantra, it's in space is dangerous, on the surface is safe. What we forget about is that on the surface is on a surface of a planet that was designed to create and sustain life for, it's a miracle. On Mars, that assumption doesn't hold. So we have to be really careful, because at Mars, being in space is probably safer initially till we get all the equipment up and running than being on the surface. And so it wouldn't surprise me if initial missions might be orbital, initial missions might be short stays. I could even envision that you might land in two different places and then use the crews to actually help validate the reconnaissance, maybe, and then really pick a Plymouth Rock and not a Jamestown, and so you could sort of see an interactive piece where you're getting science from two different sites, but you're also doing site selection work with those human beings, and it may not be until the permanent base isn't picked until after those initial missions. They could be very easily follow that sequence.
Well, it sounds like you have a difficult decision ahead of you and everyone involved, and on the one hand, I'm very envious that you get to sit around and look at all of these things and brainstorm and think about the pros and cons and have these conversations. But at the same time, obviously, it's going to be a very difficult decision, and that I'm not envious. Rick, thank you so much for taking the time to chat with me today. Yeah.
Can I say one thing? I don't mean to interrupt.
Yeah, of course. Yeah.
So it is difficult, but there's an amazing collection of forward-looking human beings all across this planet that are trying to figure these things out. And it's a mistake. And I'm not saying you were saying this, but it's not a one person, it's a we, and that we vet all these ideas. And I know you get that, but I get nervous about it when I worry about, what I might have to do or whatever, but I have total confidence in that we to actually come up with a good 90% answer for the next steps. And we'll figure it out. And before long, we'll become a multiplanetary species.
Yeah. But it feels, like just to name it just feels this, it's this decision that has been percolating for so long, and finally get to the point, go like, this is it, this is the place, and start really dreaming of what that future looks like has got to be both kind of exciting and terrifying, just like going to Mars. Yeah. Rick, thank you so much for taking the time to chat with me. Good luck with your decision process, and please, when you do decide on the name, will you let me know?
Yeah, absolutely.
All right.
Take care, man.
Thank you so much.
Have a great weekend. Bye.
All right, you too. Bye-bye. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content that we don't publish anywhere else. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Tim Whalen, Dave Verabioff, Joff Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.